right, the roster method for representing sets would be this right here. Suppose that I define set A to be equal to this set that contains these 5 elements here. 1, 2, 3, 4, 5. So we have an open brace and a closed brace. Roster notation makes use of braces. And inside the braces are the elements or the objects that belong to the set. This, ladies and gentlemen, is called a finite set. It's called a finite set because we have a finite number of objects or items or elements in the set here. Okay. All right. We would say that 1 is a member of set A. This symbol in set theory is to be interpreted as the words is a member or belongs to, is a member of or belongs to. Okay. 10 is not in the set. So 10 does not belong to or is not a member of set A. Putting a slash through this symbol means is not a member of or does not belong to set A. Does that make sense here somewhere? Okay. That's one way to represent a set, roster method. Here are a couple more sets using roster method. The set of natural numbers. Is usually denoted by an uppercase N. And the set of natural or counting numbers, ladies and gentlemen, are the first numbers we run into in our lives. It would be the set consisting of 1, 2, 3, 4, 5, 6, 7, on and on this goes. So we put what's called an ellipsis here. These dots indicate that this set goes forever to the right. And so, ladies and gentlemen, this would be an example of not a finite set. This is called an infinite set because there's an infinite number of elements or objects that belong to this set. This goes forever to the right. All right, the set of integers. The set of integers is usually denoted by this Z, this script Z here, the set of integers. And the set of integers would be the set consisting of all integers that go to the left forever. So negative, I'll pick up at -4, -4, -3, -2, -1, 0, 1, 2, 3, 4, and it goes to the right forever. So this is obviously an infinite set here, okay? That's the roster notational way of representing a set of all integers. It too is an infinite set. 2/3 is not an integer. So we would say 2/3 would not belong to the set of integers or would not be an element of the set of integers. Okay. Just like -5 would not be an element or would not belong to the set of counting numbers or natural numbers. But -5 would belong to the set of integers. Any questions with any of this symbolism surrounding sets so far, ladies and gentlemen? So that's the roster way of representing sets by enclosing the elements of the set within braces, whether the set is finite or infinite. All right, any questions about this page? Another way to represent sets is what is called the descriptive method. I could define a set to be the set of all natural numbers less than 10. Notice the descriptive method for representing a set includes words. Okay, it kind of describes in words the set of numbers we're talking about. So this would be describing all counting numbers or natural numbers that are less than 10. So in roster notation, that would be the set consisting of 1, 2, 3, 4, 5, 6, 7, 8, and 9, correct? All right, here's another one. All even numbers greater than, all even numbers greater than 0 and less than 14. That is a descriptive method for representing this set of numbers. And of course, this set would consist of, first of all, in roster notation, this set would be 1, 2, 3, 4, 5, 6, 7, 8, 9. This set in roster notation would be all even numbers greater than 0 and less than 14. So it would be 2, 4, 6, 8, 10, 12. All righty. There's another way, ladies, I'm going to represent a set of set. It's called set builder notation or set builder method. This is the third way of representing sets. It makes use of braces like all the other ones do, but it makes use of a variable. So set builder notation, I could give you an example that says this. Set builder notation is all numbers x such that x has to be a natural number and x has to be less than 10. This is called set builder notation, way of representing a set. Again, it's read as the set of all numbers x such that, this vertical bar means the phrase such that our number x has to belong to the set of integers, excuse me, the set of natural numbers or counting numbers, and must be less than 10. So roster notationally speaking, this set would consist of what? The elements 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right, let's give ourselves some set to work with, and let's try to describe this set 3 different ways. Suppose I give us these elements 32, 33, 34, 35, ... So is this a finite or infinite set here? What would be your guess? Finite or infinite?
Would it be infinite?
Yeah, it's infinite because these dots indicate it goes forever to the right. What do you think the next number would be next to 35?
36, 37, 38, 39.
Just keeps going. Okay. Now we're going to try to describe this set or represent the set 3 different ways. Roster notation. All right. So what would be the roster way of representing this set? Well, that would just be enclosing these numbers inside braces. That's the roster method for representing the set. The descriptive method, how could we in words describe these numbers? Anybody? How could we in words describe these numbers? Well, they are natural numbers, are they not? We could say all natural numbers greater than 31. There you go, ladies and gentlemen. That'd be a descriptive way of representing a set of numbers. All natural numbers that are greater than 31 would be 32, 33, 34, 35, 36, 37, etc., etc. Set builder notational way of representing this set. Open brace, we'll use a variable. It's the set of all numbers x such that x has to be a natural number. So it has to belong to the set of natural numbers. And x has to be greater than 31. Or you could have said greater than or equal to 32. That would also suffice. Questions how we represented that set 3 different ways. All right, any questions about anything on this page here? All right, now I'm going to define for you an important set that does occur quite a bit. So this is a definition of what's called the empty set. The empty set. The empty set is the set with no elements or objects in it. Ways of representing the empty set, ladies and gentlemen, would be an open brace and a closed brace and nothing inside. That represents literally the empty set. The set is empty. Or another way to represent the empty set is to put a circle with a slash through it. This means the empty set. Would this set be empty? The set of all objects X, such that X is a human living on planet Mars. Ladies and gentlemen, would there be anything in this set? The set of all objects such that X is a human living on Mars. Would there be anybody in this set? Well, not to my knowledge. I don't think there's anybody living on Mars. If there is, that's news to me. So this would be what? The empty set. Or we could say this set is empty. Make sense? All right. How about some operations with sets now? What is the union of sets? How do we, undertake the union of sets? The union of sets is the joining of sets. When we join sets together, we provide the union of these sets. It is the joining of sets. Sets. If I define set A to be the set that consists of 3 elements or 3 objects, 2, 3, and 4, and I define set B to consist of these 4 elements or objects, 10, 20, 30, and 40. All right, ladies, let's have a little bit of fun here. What would be the union of these sets? Now, the union is denoted symbolically as this U symbol. So we read this notation as A in union with B, or the union of sets A and B. The union of sets A and B is going to form a set that basically joins sets A and B elements together. So A union B is going to be a bigger set that consists of all the elements from set A plus all the elements from set B. That's called the union of sets A and B. What's the intersection of sets? The intersection of sets is a set that only contains objects common between both sets. And the intersection symbol, ladies and gentlemen, is the upside down U. So we read this as A intersect B, or the intersection of sets A and B. Now let me ask you this question here. Are there any elements in set A that are common to set B elements? Are there any elements that are shared by both sets? The answer is no. So the intersection of sets A and B would be the empty set, or we would use this to denote the empty set. Any questions about union or intersection of sets? All right. Suppose, ladies and gentlemen, I define set A to be the set that consists of the elements 1, 10, 90. And I let B be the set consisting of the elements 10, 90, 200, 300. Both of these are finite sets. Suppose I want you to find A intersect B. What would that be? What elements would have to be in the intersection of these two sets? Anybody? What elements are common between both sets? Well, after a little thought and inspection, we would discover that 10 and 90 are the only elements that belong in the intersection of these two sets because they're the only elements that are shared by both sets. Any questions about that? What is the cardinality of a set? The cardinality of a set. The cardinality of a set is the number of objects or elements in the set. In other words, if I define set A to be the set that consists of -5, -3, 100, 1000, what would be the cardinality of set A? Symbolically, we represent the cardinality of a set by this notation. This is basically saying how many elements are in set A? What are the number of elements that are in set A? Well, the number of elements are 1, 2, 3, 4. There's 4 elements in set A. That'd be the cardinality of set A, 4. Any questions about what cardinality is, ladies and gentlemen? All right, now we're going to get into what's called a Venn diagram. A Venn diagram is a pictorial way of representing sets. It's a picture way of representing or of depicting sets. So all right, this box here basically encompasses what's called the universal set. U for universal. U equals universal. It basically encompasses everything that's under investigation. For instance, if I was interested in all the students at Mott Community College in an investigation, my universal set would consist of all the students that attend Mott Community College. What if I call this set 1 right here, and I call this set 2? And this is set 3 right in here. And this is set 4 out here. Now, what does set 1 represent? What does set 1 represent here? Set 1 is all elements in set 1. Set 2 represents all the elements in set 2. What does set 3 represent? Set 3 represents only elements that are common to both sets and 1. Set 3 is the intersection of sets 1 and 2. It's the intersection of sets 1 and 2. Set 4. Set 4 consists of all elements in the universal set that are not in sets 1, sets 1 or 2. So out here in set 4 consists of all elements that belong to the universal set and yet are not found in set 1 or 2. Any questions about that? All right, now that we're armed with that knowledge, I'm going to see if we can go to our textbook and have a little bit of fun now. We're going to go grab our book. Just bear with me, I have to log in. All right, so we're going to go to the appendix. This section hangs out in appendix, back in the appendix 13.1, entitled sets. Okay. All right, so we're going to go down where the problems begin. All right, let's get into problem, start with problem 13A here. How many elements does the following set have? In other words, what's the cardinality of this set? How many elements are in this set here? Well, after a little visual inspection and thought, you can count how many elements are in here. 1, 2, 3, 4, 5, 6. There's 6 elements in this set here, 13A. All right. Now, for a number 14, they give you a set that consists of 3 elements, 12, 22, and 32. And they want you to form a subset, ladies and gentlemen, that has 2 elements in it, 1 element, and 3 elements. Okay. What does that mean? Well, a subset is a set that consists of no more than the number of elements that are in the parent set. So we would call this like the parent set. Or, ladies and gentlemen, we could call it the universal set. Call this like set A. Now, if I form a set B here that consists of only 2 elements in it, maybe like the elements of 12 and 22, we say B is a subset of set A. B is a subset of set A. And we would denote that symbolically, we would represent it this way. This is saying that B is a subset of set A. And this happens to be a proper subset. We say B is a proper subset of set A because its cardinality is less than the cardinality of set A. So in other words, every element in set B also belongs to set A. That's why we say set B is a subset of set A. Okay. Suppose I form another set, C, that consists of just maybe 1 element from this set, like 22. Well, every element in set C belongs to set A. So we can say that set C is also a subset of set A. Set D, which consists of 12, is also a subset of set A. Set E, which consists of the element 32, would also be a subset of set A. Now, suppose we form set F, which consists of all elements that are in set A. Well, we would say that set F is basically a subset of set A, but we also put this little flat line underneath the subset symbol because that indicates that not only is every element in set F also in set A, which it is, but it's also true that the cardinalities of these sets are equal. The number of elements in set F is equal to the number of elements in set A. So when the cardinality of two sets are equal and one subset's a subset of the other set, then we would have to use this little horizontal bar underneath our subset symbol. Basically, you can see that set F really is set A. They really are the same sets. Not only do they have the same elements, they have the same number of elements. Their cardinality is the same. Okay. Oh, there's a nice important fact in passing. The empty set is a subset of any set. It's always true that the empty set is always a subset of any set. So the empty set would be a subset of set A. The empty set would be a subset of set A. The empty set would be a subset of set B. The empty set would be the subset of set C. The empty set would be a subset of set D. The empty set is a subset of any set. Okay. Any questions about any of this on this page here? All right, let's go back to the book. Tell whether each of the statements is true or false. The set of integers is a subset of the set of whole numbers. Is that true? Is every integer a whole number? Is that true or false? Is the set of integers a subset of the set of whole numbers? In other words, is every integer, and there's an infinite number of them, also a whole number? Is it true to say the set of integers is a subset of the set of whole numbers? The set of whole numbers being 0, 1, 2, 3, 4, 5, etc. Is that true, ladies and gentlemen? Is every element in the set of integers also in the set of whole numbers? The answer is no. You have a lot of negative integers, don't you? And no negative integers appear in the set of whole numbers. This is not true. We would say the set of integers is not a subset of the set of whole numbers. The set of integers is not a subset of the set of whole numbers. Is the set of whole numbers a subset of the set of integers? Is that true? If I spin it around, is every element in the set of whole numbers also in the set of integers? The answer is yes, it is. This is true. So this, Liz, I'm going to say the set of integers is a subset of the set of whole numbers is a false statement. But to say the set of whole numbers is a subset of the set of integers is a true statement. Any questions about the differences there? All right, B, 15B, the set of natural numbers is a subset of integers. Is every natural number also an integer? Is every natural number, which is 1, 2, 3, 4, 5, 6, 7, all the way onwards, upwards, also in the set of integers? The answer is yes. So therefore, the set of natural numbers is indeed a subset of the set of integers, because every natural number is also an integer. You know, we could represent the relation between all these sets of numbers that we work with in our mathematics course by using a Venn diagram. We have the universal set out here, and then we have a subset of the set of universal set numbers, which is called a set of real numbers. So this is all the set of real numbers here. The set of real numbers has two smaller subsets embedded in it. It has a set of what are called rational numbers versus the set of irrational numbers. There's a smaller subset of numbers that sits inside the set of rational numbers. It's called the set of integers. There's a smaller subset that sits inside the set of integers. It's called the set of whole numbers. And there's a smaller subset that sits inside the set of whole numbers. It's called the set of natural numbers. This Venn diagram gives you a bird's eye view as to the relationship of the sets of numbers we play around with mathematics. The universal set, ladies and gentlemen, is a set consisting of a larger set of numbers that engulfs the set of real numbers. It's called the set of complex numbers. We don't study complex numbers in Math 07-2. You will when you get an intermediate algebra and beyond. Okay. This is a Venn diagram that gives us a pictorial relationship as to the set of numbers and how one set's a subset of the other set. So, ladies and gentlemen, we would say that it's true that the set of natural numbers is a subset of whole numbers, which is a subset of the integers, which is a subset of all the real numbers. This is a true statement. Every natural number is also a whole number, which is also an integer, which is also a real number. Okay? That's a true statement there. I mean, is it true to say in 15C that the set consisting of 1, 7, 14, and 26 is equal to the set consisting of 14, 1, 26, and 7? Are these sets equivalent to each other? Well, in order for sets, yeah, what were you going to say?
Yes, they are.
Yeah. Yeah, for sets to be equal to each other, two things have to be true. Number one, both sets have to have all the same elements in them. Every element in one set has to also be has to also be found in the other set, and vice versa. Number two, the cardinalities of the sets have to be the same. They have to have the same number of elements. And notice, not only are all the elements in the left set in the right set, and vice versa, but each set has a cardinality of 4. There's 4 elements in each set. So those are equivalent sets. That's a true statement. All right. Okay. All right, let's start getting down in here into some of our Venn diagrams here. Let's look at this Venn diagram for problem 61 here. They give you a Venn diagram here. They give you a universal set, which is the contained inside this rectangle here. And they give you this set A that consists of these elements, these numbers, and set B that consists of these numbers. And notice there are some numbers outside of both sets A and B that are found in the universal set. Now, what would be the intersection of sets A and B? 61A would be what set? What's the intersection of sets A and B? What elements would be in the intersection of set A and B? Can you name off the elements that would be found in the intersection of A and B?
Wouldn't it be 0, 2, 4?
0, 2, and 4. That's it. That is correct. That would be the intersection of sets A and B here. It would be only the elements of 0, 2, and 4. That would be the intersection. Those are the only elements common to both sets A and B. In part B, what would be the union of these two sets, A in union with B? Now, if we join these sets together, well, it's going to be a bigger set consisting of all the elements in set what? A. and all the elements in set B. So that would be 0, 1, 2, 3, 4, 5, 6, 7, 9, and 12. Do you agree? So the union of those two sets would be the set that joins together all the elements from both sets. That would be the union. Do you understand the difference between intersection and union? What is the universal set? What would be in the universal set? Anybody? What elements would be found in the universal set?
8, 13, and 14.
And also all the elements found in set A and what? B. Do you agree?
Yes.
Because set A is a subset of the universal set. So is set B. It's a subset of the universal set. Because every element in A is also found in the universal set. Every element in B is also in the universal set. So the universal set would be the set consisting of 0, 1, 2, 3, 4, 5, 6, 7, 9, 12, 8, 13, and 14. Do you agree?
Mhm.
Which numbers for part D here, which numbers belong to neither set A nor set B? What numbers do not belong to A or B? You would say? What elements do not belong to sets A or B? You would say that's the set consisting only of what elements?
8, 13, and 14.
That's it. 8, 13, and 14 are the only elements that are excluded from sets A and B, and yet they are found in the universal set. Okay. All right, that makes sense, that question there, Lizzo? All right. Okay. Now, in problem 63 here, they define for you using roster notation what the universal set is, what set C consists of and set D consists of. And they want you to place the numbers in the proper locations in this diagram, this Venn diagram here. So let's start with the intersection of sets C and D. What elements would go in the intersection region of sets C and D? What would I put in the intersection of sets C and D there? Well, those would be the elements that are common to both sets, what, C and D, right? And what elements are common between sets C and D, which really means we're finding the intersection of sets C and D. 1/3 is in D and 1/3 is also in C. So 1/3 would be found in the intersection of C and D. 2/3 is in set D, but it's not in set C. 2/3 would not be in the intersection of sets C and D. 4/3 is in set D, but it's not found in set C. So 4/3 would not be in the intersection of sets C and D. Neither would 1/4 or 1/5. So there's what's the only fraction found in the intersection of sets C and D? That would just be 1/3. Everybody see that there? 1/3. But there are also elements that belong to set D that are not in the intersection of set C and D. We already counted for the 1/3, but 2/3 and 4/3 are also in set D, although they're not in the intersection of set C and D, they are in set D. So we have to put 2/3 and 4/3, what? 2/3 and 4/3 would have to be out here. Because 2/3 and 4/3 are also found in set D, although they're not in the intersection of sets C and D. So 2/3 and 4/3 are found in set D, but not found in set C. In a similar way, there's a lot of other elements that belong to set C that are not in the intersection of set C and D. We already accounted for 1/3 being in set C and also the intersection of C and D. But how about 1/2, 1/4, and 1/5? Those are elements in set C, and yet they're not found in the intersection. So we're going to have to list those elements in set C out here, 1/2, 1/4, 1/5. Is this making sense how we're putting the elements where they belong? But ladies and gentlemen, there's a lot of elements in the universal set. Look at them all. Which ones have been accounted for in sets C and D, or the intersection of sets C and D? Which ones we've already accounted for that are also in the universal set? Well, 1/3 we accounted for. 1/2 we accounted for. 1/4 we accounted for. 1/5 we accounted for. We did not account for 1/6. So 1/6 has to be in the universal set, and yet not in set C or D. 1/7 is not found in set C or D, but it is in the universal set. So it has to be out here in the universal set somewhere out here. 2/3 is in the universal set. 2/3 was also in set D. We already accounted for that. 4/3 is in the universal set, but we already accounted for it in the fact that it's in set D. So there you go, ladies and gentlemen. This would be the Venn diagram for those sets. Everybody understand the Venn diagram? Notice every element in set D is in the universal set. So we would say that set D is a subset of set C. Every element in set C is found in the universal set. So set C is a subset of, wait a minute. Every element in D is found in the universal set. So set D is a subset of the universal set. Every element in set C is found in universal set. So the set C is a subset of the universal set. Okay. Does that make sense? Would it be fair or accurate to say the universal set is a subset of set D? Is that true? Is that true? Is that saying every element in the universal set's also in set D? No, no good. There's a lot of elements in the universal set that are not in set D. 1/4, 1/6, 1/4, 1/5, 1/2. Universal set's not a subset of set D. Set D is a subset of set U, though, the universal set. Right. Any questions about how we're working with these Venn diagrams here so far? Okay. Now, here they want you to match each statement with the correct Venn diagram. So, ladies and gentlemen, they're giving us some Venn diagrams here, and they want us to match them with the correct statement. All right. So how are we going to do that? Well, in order to do that, we are going to run into another set operation called the complement of a set. The complement of a set. The complement of a set is the set that contains all elements in the universal set that are not in the set. All the elements that are contained is a set that contains all elements in the universal set that are not in the set in question. Okay, let me show you an example. Suppose, ladies and gentlemen, I define set A to be the set that consists of 1, 2, 3. I define the universal set to be the set that consists of 1, 2, 3, 4, 5, 6. So we could build a Venn diagram to represent this situation. There's set A. And the universal set consists also of 4, 5, and 6. Okay. All right. We read this notation here with this little we read this notation here, ladies and gentlemen, with this little apostrophe or dash up here. We read this as the complement of set A. Complement of set A. The complement of set A is going to be a set consisting of all the elements that are in the universal set that are not in set A. So what are all the elements found in the universal set that are not found in set A? Well, 4 is in the universal set, but 4 is not in set A. So 4 would be found in the complement of set A. 5 is in the universal set, and yet 5 is not found in set A. So 5 would also be in the complement of set A. 6 is in the universal set, but 6 is not found in set A. So 6 would also be in the complement of set A. So again, the complement of a set is a set consisting of all elements that are found in the universal set that are not in set A. That's called the complement of set A. Any questions about the complement of a set? All right, let's go back to our textbook and try to do this problem here. So I have a question. If you look at Venn diagram I there, this first one here, the shaded region, ladies and gentlemen, represents the elements in the set of interest. For instance, notice this first Venn diagram here in I here only has the region shaded outside of sets A and B. So the set that is being depicted by this Venn diagram is a set of all elements that belong to the universal set and yet do not belong to set A or B. So this shading out here represents all elements that are in the universal set that are not found in A and they're not found in set B. So what does that mean? Would that be A and B? That would not represent A and B because A and B would only include the region of overlap between sets A and B. So A and B would be A intersect B. And means the same thing as intersection. All right, let me show you this here. A and B. The word and means the same thing as intersection between sets. So A and B means the same thing as A intersect B. The word or means the same thing as union. So A or B means the same thing as A in union with B. So what would be A and B? What would be the Venn diagram representation of A and B? This is set A, this is set B, this is a universal set. A and B really means the same thing as the intersection of sets A and B, which would be this region in here. This, ladies and gentlemen, is A and B. It's A intersect B. You see that there? It's a set that consists of only elements that are common to both sets A and B. What would be A or B? Well, A or B is A in union with B. So Venn diagram, grammatically speaking, how would we represent A or B? Remember, union joins sets together. So if we join all the elements in sets A to all the elements in set B, we have a bigger set. So to represent A or B, we would shade sets A and B, shade them all. This represents the union of sets A and B. Every element in this shaded region belongs to the union of sets A and B. Every element in the shaded region here belongs to the set A intersect B. Do we understand the Venn diagram representation of the intersection or the union of two sets? What would this be? What would the complement of set A be? How would we shade the region that would contain all elements that are found in the universal set that are not found in set A? This is set A. This is set B. This is your universal set. How would we graph or represent using a Venn diagram all elements that are found in the universal set and yet not found in set A? Well, to not be in set A, we would have to shade outside of set A. We would have to shade everything outside of set A. You are looking at the Venn diagram that would represent the complement of set A. It consists of every element in the universal set that's not in set A, not in set A. Does that make sense? What would be the Venn diagram for B complement or the complement of set B? Well, that's got to be every element found in the universal set that's not found in set B. So to represent the Venn diagram of the complement of set B, we would shade every region that's outside of set B. This would be the graph or the Venn diagram that represents all elements that are in the universal set, but are not in set B. That's called B complement, okay? All right, so that's what complement is. All righty. So what would be the Venn diagram that goes with A and B? Well, that would be this diagram here, I. What would be the Venn diagram that goes with A or B? Well, that's the joining of sets A and B together. It'd be I, the Venn diagram on I. What would be the complement of sets A or B, ladies and gentlemen? Well, that has to be every element in the universal set that's not in set A and not in set B. That would have to be this Venn diagram up here. This represents the complement of sets A and B. It consists of all elements in the universal set that are not found in sets A or B. Now, what does it mean to say that sets A and B are disjoint sets? Well, to say two sets are disjoint means that the sets have nothing in common. Nothing in common, ladies and gentlemen, meaning the sets cannot overlap anywhere. So to say that set A and B are disjoint sets means that set A and B would have to be drawn separate from each other where there cannot be any overlap between sets A and B. So the Venn diagram that goes with number 65 would be this one here. That's saying sets A and B are disjoint. There's nothing common between these two sets here, okay? Oh, so the complementary set can be represented with the little hyphen that I've been using, or the apostrophe, or it can be represented with a bar over the set. So another way to represent the complement of set A is to put set A and put a bar above it. The complement of set B is B with a bar above it. Just a matter of notation. Means the same thing as what I'm saying here. The complement of set A, complement of set B. All right. All right, so that gives us a little idea, ladies and gentlemen, as to some of the jargon surrounding set theory here a little bit, okay? And I'm not going to go into great detail with this set theory here. I just want to give you a little bit of a snapshot as to some of the most common, popular, basic things surrounding sets. Alrighty, so this hangs out in Appendix 13.1. All right, so we're going to move out of this now, and we're going to go into Chapter 10. We got two sections in 10 to cover. 10.1, which addresses the addition property of equality, and 10.2, which addresses the multiplication property of equality. And what we're going to do is we're going to start learning how to solve what are called linear or first degree equations, okay? And a large part of your time spent in any mathematics course involves solving equations in mathematics. So 10.1 warms us up to using what's called the addition and the subtraction property of equality. All right, so we're going to learn how to start working with what are called equations in mathematics. All righty. Let me give you some examples of some equations. This is called an equation in mathematics, ladies and gentlemen. It's not an expression, it's an equation because we see the equal sign. Here's another example of an equation. That's an equation. This is an equation in mathematics. Okay, all these are equations. And what do we do with equations? Well, what we do with equations, ladies and gentlemen, is we solve equations. We solve equations. We don't simplify them. We don't evaluate them. We solve them. Okay. What does it mean to solve an equation? Well, to solve an equation means to find what number or numbers, as the case may be, satisfy the equation. Or make it a true statement. Let's give ourselves an equation to work with, just a simple one. X plus 2 equals 5. This is an equation, ladies and gentlemen. Suppose I just choose a number out of thin air, and I ask ourselves this question. Is X equal 1 a solution to this equation? Is X equal 1 a solution to this equation? Well, to find out, we're going to replace the X variable in the equation with 1. And we're going to ask ourselves, is 1 plus 2 equal to 5? Is this true or false? Is 1 plus 2 equal to 5? Is 3 equal to 5? Is that true or false? That's false. So therefore, we would conclude that 1, or X equals 1, is not a solution to this equation. It's not a solution to this equation. It doesn't satisfy the equation. Can anybody give me, just by visually looking at this equation, can you give me a solution to this equation? Can you think of what number X would have to be equal to, ladies and gentlemen, for this to be a true statement?
3.
Yep, X would have to be equal to 3. In fact, 3 is the only number that X could be equal to if this is to be a true statement. Because if X is equal to 3, we see that 3 plus 2 is indeed equal to 5. So we would say the solution to this equation is X equals 3. This is the solution. And the only solution. All right. Now, granted, these equations are pretty simple now today, where we can just basically sit back and just visually eyeball it and determine what the solution is visually. But ladies and gentlemen, that's not always going to be true. Sometimes these equations are going to become more advanced, in which case we're not going to be able to just sit back and eyeball them and determine what the solution is. We need a more orthodox, organized approach to solving equations formally. And that's what we're going to get into now. How do we formally solve this equation for its solution of 3? How do we algebraically demonstrate legal steps to get to the solution? That's what we're going to start to show you, and hopefully you can start to adopt the methodology I'm about to portray. All right. In order to solve equations, we have to warm ourselves up to, first of all, what are called properties of equality. Okay, properties of equality. And we also have to arm ourselves with what are called inverse operations in mathematics, or inverses. Suppose that I start off with a number 9 and I don't want anybody messing around with my number 9. I want it to stay 9 forever. But so suppose somebody comes along and messes with my 9, they add the number 3 to it. Well, I no longer have 9. How can I get my 9 back, ladies and gentlemen? How can I undo what's been done to my 9? How can I undo the adding of 3 to my 9? I want to get my 9 back. What's the undoing of addition? Anybody? What's the inverse operation of addition? Well, what I can do is turn right around and subtract that 3 right back off, and I'll get my 9 back. Agree? Anybody see that there? Or if I start with the number 9 and somebody starts messing with it and they subtract 2 from it, I no longer have my 9. How can I undo what's been done?
You add 2.
I could add 2 right back to it and get back my 9. Everybody see that there? So ladies and gentlemen, we're discovering very rapidly that addition and subtraction are inverses of each other. They undo each other. The undoing of addition is subtraction. The undoing of subtraction is addition. All right, that's one thing we need to understand. Here's another thing. We now need to understand what's called the addition property of equality. The addition property of equality can be illustrated with this example. Suppose I give ourselves a true statement to work with. 5 is equal to 5. Do you agree? That's true? That's true all day long. Do you agree? Suppose, ladies and gentlemen, somebody comes along and messes with my equation here. Suppose that they add 3 to the left side of my equation. Well, guess what? I now have a false statement. My truthful statement or equation becomes a false equation. I have a question for you. What could I do to the right side of my equation to resurrect this situation, to get back a true equation? More specifically, what could I add to the right side of my equation so that the right side would once again be equal to the left side? What do you think? Well, if somebody comes along and adds 3 to the left side of my equation to get back a truthful equation or a truthful statement, I could turn around and add the same number to the right side. Do you agree? And I would once again get back my true statement, my true equation. This, in a nutshell, is illustrating what's called the addition property of equality, ladies and gentlemen. It says this: if A is equal to B, then it is true that if you add some number C to the left side and the right side of the equation, you still maintain equivalence. This illustrates what's called the addition property of equality. If A equals B, then A plus C is still equal to B plus C. As long as we add the same number to both sides of our equation, we maintain equivalence. That's called the addition property of equality. That's true. In a similar sense, here is called the subtraction property of equality. The subtraction property of equality says that if A equals B, if I have this true equation, and somebody comes along and let's say subtract some number C from the left side, well, how would I maintain equivalence? I would also have to subtract the same number from the right side of my equation. This illustrates the subtraction property of equality. As long as you subtract the same number from both sides of your equation, you still maintain equivalence. Do we understand what those properties are saying there, ladies? These properties are going to enable us to solve equations in section 10.1, basic equations. So let's begin to do this now. Let's just dive right in. Let's give ourselves an equation to work with here. All right, here we go, ladies and gentlemen. We want to solve this equation. Notice the instructions say not simplify, not evaluate. It says solve. I want to solve this equation for X. So in order to solve an equation, we need to get the variable all by itself on one side of the equation. That's our goal. Because if I get the variable on one side of my equation, then my solution will be on the other side of the equation. That's what we're shooting for, to get the variable all by itself. That's to say we got to get X all by itself. That's to saying that the number being multiplied in front of X has to be a positive 1, has to be. That's saying X is by itself. So ladies and gentlemen, presently I have 1 times X here on the left side, but I have something in the way of X being all by itself on the left side. I got 2 that's being added to X. How can I get X all by itself on the left side of my equation? How can I undo the addition of 2 to X? What's the inverse of addition?
Subtraction.
Subtraction. So the undoing of this 2 that's been added to my X, in other words, to get this X all by itself, I'm going to undo the addition of 2. And I'm going to do that, ladies and gentlemen, by subtracting 2 from both sides of my equation. If I subtract it from the left, I must also subtract it from the right, in keeping with the subtraction property of equality. That property says that as long as I subtract 2 from both sides of my equation, I still maintain equivalence between the left and the right side. Now, what happens to the 2's on the left side? What's 2 minus 2? What happens to these 2's?
0.
0. They become 0. And technically, we have X plus 0 on the left side is equal to 7 minus 2 or 5 on the right side. Well, X plus 0, anything plus 0 is still itself. So X plus 0 is still X. And ladies and gentlemen, we're done. We call 5 the solution to our equation. That's your solution. We solved this equation and we got a solution of 5. You know, when you solve an equation, you can always check your answer if you want to. I'm not going to require that, but you can. You could take the 5, substitute it back into the original equation for X and see if you get a true statement. Is 5 plus 2 equal to 7? Does it work? And it does check out. Do you agree? That's why we say 5 is the solution and the only solution to that equation. Does everybody understand how I formally, ladies and gentlemen, solve that equation using my equality property of subtraction? So showing the step on your paper is something very important. And I would expect you to show this step on a future quiz or exam. If I give an equation like this and say solve for X, I want to see this step that's showing me that you understand that you need to subtract 2 from both sides to get X all by itself. Very important step. I'll be looking for that step. Are there any questions about that? How we solve for X? All righty. Maybe we could try another one, huh? Now, the variable does not always have to be X. Sometimes the variable, it could be any variable. How about T? What if we have T minus 11 is equal to negative 20? And we want to solve this equation for the variable T. Well, how do I get T all by itself on the left side of my equation? How do I undo the fact that 11's been subtracted from T? What's the inverse of subtraction?
Addition.
I'm going to add 11 to the left side of my equation. But if I add 11 to the left side, I must also add 11 to the right side. So I maintain equivalence in accordance with the addition property of equality. Notice the 11's on the left side add up to 0. Negative 11 plus 11 is 0. We say the 11's cancel out. They're gone. And we're left with T. And what's negative 20 plus 11 on the right side? What is a negative 20 plus a positive 11?
Negative 9.
Negative 9 is the solution to this equation, and we're done. We have solved that equation. Is this making sense how we're solving basic equations, ladies and gentlemen, by utilizing either the addition or the subtraction property of equality? Is this making any sense here so far?
Mm-hmm.
All right. Any questions so far? How we're solving these basic equations here. All right. Now, you think the equations are always going to be this simple? Well, it'd be great if they were. But unfortunately, that's just not going to be the case. But eventually we will get up to more advanced equations, but we have to learn how to crawl before we learn how to walk, before we learn how to run. Let's try another one. Oh no. Do you think fractions are possible in an equation? You betcha. You could have fractions, you could have decimals. All right, ladies and gentlemen, we want to solve this equation for the variable C, which means I have to get C all by itself on the right side of my equation. I need to get rid of this 4/5 that's being subtracted from C. What's the inverse of subtraction? What undoes subtraction?
Addition.
So I'm gonna have to add 4/5 to the right side of my equation. And then I'm also gonna have to add it to the left side of my equation. Gotta add 4/5 to the left side. Addition, property of equality. Now on the right side, the 4/5 cancel out the 0. They're gone, leaving us with C, and that's what we want. C all by its lonesome on one side of our equation. Unfortunately, we got to add some fractions together on the left side. But ladies and gentlemen, you get to use your TI-30 or TI-34. Can anybody dial this up? What is -7/8 plus 4/5? Because that's going to be your solution. If you want to do this a long way, you can find the least common denominator is 40 and then go from there. Multiplying top bottom of this fraction by 5 would crank out -35/40 as being an equivalent fraction of -7/8. Multiplying top bottom of this fraction by 8 would crank out an equivalent fraction of 32/40 for 4/5. And now we just add our numerators together. What's -35 plus 32 over 40? This implies, ladies and gentlemen, that -3/40 would be the solution to this equation. That's what C has to be equal to. Any questions how we formally solve that equation using legal algebra? Everybody understand that this step is very important here. Make sure you show me this step, because this step is showing me that you understand that you need to add 4/5 to both sides of your equation to get C by itself. Very important. I'll be looking for that step. Everybody understand how we solve this for C? Yes, there can be fractions. They do occur in equations. You can get all types of situations in equations. Okay. Now, there might be times, ladies and gentlemen, when we have to simplify one and or both sides of our equation before we utilize the addition or subtraction property of equality. It happens all the time. So suppose that I have this equation here, 2 minus 3x plus 4x. And that's going to be equal to, let's say, like 24. I want to solve this equation for x. This one is a little bit more complicated, but our goal remains the same. We got to get x all by its lonesome on one side of our equation, preferably the left side, and our solution then will be on the right side. But how do we get there? How do we legally, algebraically get there? Well, the first thing I have to do, ladies and gentlemen, is I have to combine what are called what? Like terms. Do I have some like terms here? Are these like terms? -3x and 4x?
Yes, I was just about to say that.
What would they
Yeah.
combine to give us? What is -3x plus 4x? What's -3 plus 4?
1.
1. So -3x plus 4x combined to give us 1x. Let's write that down. Oh, don't forget to bring this 2 down. And it's understood, ladies and gentlemen, that since -3x plus 4x combined to give you a plus 1x, there would be a plus sign in between the 1x and this 2 that's still on the left side of your equation. Don't lose that. See how we simplified the left side by combining like terms. All right, now what we got to do is get x by itself. X is not by itself because we have what? What kind of a 2 is being added to 1x here? What sign's in front of the 2? I don't see a sign, so it's understood to be what kind of a 2? Positive or negative?
Okay.
It is understood to be a positive. And you know what? If you don't like the way this left side's written, you can spin these terms around. It's legal to do that. Instead of saying 2 plus x, we could spin this around and call it x plus 2. Still the same thing. Still the same equation. You can spin these terms around. Now it's easy to see what we need to do. How do I get x by itself? How do I get rid of this 2 that's being added to x?
Subtract.
We're going to subtract off 2 now from the left side and from the right side of our equation. The 2's drop out on the left side to 0, leaving you with x plus 0, which is just x. And on the right side, we have our solution. 24 minus 2 is 22. And ladies and gentlemen, we are done. We have solved that equation for x, and x is equal to 22. Does everybody understand what just happened in solving that equation? To recap, first of all, we simplified the left side by combining like terms. And then we utilize the subtraction property of equality to get x by itself by subtracting 2 from both sides. Do you think that's something you might be able to do, is solve an equation like that in the future? Now watch this. Sometimes, ladies and gentlemen, we have our variable appearing on not just one side of our equation, but both sides. What if we have like 4x minus 5 is equal to 3x plus 10? And we want to solve this equation for x. Now notice x appears on both sides of our equation, and that's not a good thing. It's not a good thing because to solve this equation, we have to have x all by itself on just one side of our equation. We have to do something. We have to solve this equation for x. Now, technically, does it matter what side you get x on, the left or the right side? The answer is no, it doesn't matter. You can get x all by itself on the left side of the equation, or you can get it all by itself on the right side. Either way, if you do things correctly, you'll get the same solution. Personally, I prefer to get the variable on the left side of the equation. That's just me. That's my personal preference. And so, ladies and gentlemen, what I'm going to do here is I'm noticing that there's nothing to do as far as simplifying the left side is concerned. These are not like terms. There's no simplifying necessary on the right side. So it's time to move terms from one side of the equation to the other. But whenever you move a term from one side of the equation to the other, like when I move this 2 over to the right side, there's a price to pay. And that price to pay is you have to think of the opposite. The opposite of plus 2 is we had to subtract 2 from both sides. So if I want to move this 3x over to the left side of my equation to join the like term of 4x, how do I do that algebraically according to our equality properties? What sign's in front of the 3x? We don't see a sign, so it's understood to be what kind of a 3x?
Positive.
It's understood to be a plus, a positive 3x. How do you move a positive to the other side of your equation? What's the inverse of addition?
Subtraction.
We're going to subtract 3x from both sides of our equation. By subtracting 3x from both sides of our equation, that's going to effectively move the 3x over to the left side to join the 4x. Let's do that. I'm going to subtract 3x from the left, and I'm going to subtract 3x from the right side of my equation. This step is critical because it's showing that we're subtracting 3x from both sides. Everybody see this step here? Why can I maintain the equivalence between the left and the right? Because I'm doing the same thing to both sides of my equation. Because I'm subtracting 3x from the right side, but I'm also subtracting that same number from the left side. Some of you are going to get that confused with this back up here. You're going to say, wait a minute. When we combine these like terms here, I added 4x to the negative 3x. Why don't I add 4x to the right side of my equation also? Can anybody address that?
There's no variable at the end of that.
You see, yeah, ladies and gentlemen, I'm just simplifying the left side here. I'm just combining these like terms on the left side. By combining negative 3x to 4x and calling it plus 1x, this equation is still equivalent to the original equation. Now, when I get down here, now I'm finally subtracting 2 from the left side. Well, then I must also subtract 2 from the right side. So please don't confuse simplifying one side of your equation with moving a term from one side to the other side of your equation. There's a night and day difference. I'm moving the 3x over to the left side to join the 4x. I'm not simplifying the right or left side of my equation. I'm physically going to move the 3x over to the left side to join the 4x. That's why I must subtract 3x from both sides. Now, what's 4x minus 3x? Those combine to give you 1x. What happens to the 3x's on the right side?
Those just cancel out.
They're gone. And we're left with 10, a plus 10, or just 10. And we got our equation down to this now. Now things are looking better. We have x on the left side. All we got to do now is just get it all by itself on the left side. So how do we get rid of a minus 5?
Add 5.
We're going to add 5 to the left side of our equation. But if we add 5 to the left side, now we must add 5 to the right side also. These 5s drop out, leaving you with x, and x is equal to 15, and you are looking at your solution to that equation. That's your solution, ladies and gentlemen. We're done with that equation. Everybody understand what just happened there? I moved the 3x over to the left side by subtracting it from both sides so it could get combined with this like term of 4x. You can't combine 4x and 3x from the beginning and call it 7x. Can't do it because these are on opposite sides of the equation. They're on opposite sides. Here we can combine these x's because they're on the same side of the equation. That's why we did combine them. But when they're on opposite sides of the equation, ladies and gentlemen, you first have to move one of the terms of x to from one side of the equation to the other side before you can actually then combine them as like terms. Do we understand the difference between what happened here, just combining like terms because we're on the same side of the equation, versus having to move this term of 3x over to the left side before we combine the 4x and the 3x? We understand the difference there? All right. You know, sometimes, ladies and gentlemen, your equations are going to start to have parentheses in them. And I like to think of parentheses as being kind of like a jail. All right. And when things are inside parentheses, I kind of think of them as being kind of like in jail. And we like to get them out of jail. In order to get rid of parentheses in an expression, we're going to have to use a very important property. And this property I'm going to demonstrate to you, ladies and gentlemen, is called the distributive property of mathematics. Distributive property. Distributive property involves parentheses, okay? Now, let's show you how this distributive property works here. If I give you this expression here, and I had you evaluate this expression, what would you do first? Order of operations? What would you do first? Order of operations. Well, we would be inside the parentheses first. So what's 3 plus 5? We do that first. What is 3 plus 5? Gives you 8. Now what's 2 times 8? 16. I claim there's another way we could have got the answer of 16. I'm going to show you that other way. That other way, ladies and gentlemen, is using this property called the distributive property. Check this out. Let's do this problem over again. But this time, I'm going to take this one factor of 2 outside the parentheses and multiply it into both these terms inside the parentheses. I'm going to take 2 times 3 first. This arrow is a good visual cue. Please use arrows when you distribute. So I'm going to take 2 times 3 plus, and then I'm going to take 2 and multiply it by the 5. Everybody see that there? You are looking at what's called the distributive property in mathematics. What I just did is legal. I'm taking the 2 and multiplying it by the 3 plus, and I'm going to take the 2 and multiply it by the 5. Now, what's 2 times 3? 6. What's 2 times 5? 10. What's 6 plus 10? 16. Oh, I got the same answer, didn't we? So, ladies and gentlemen, this is called the distributive property. And notice when I distributed this 2 inside the parentheses were removed. We got the 3 and 5 out of jail. Isn't that cool? It's called the distributive property. It's used all the time in algebra and beyond. Any questions about the distributive property? What just happened here? So formally, this is the distributive property. If you have a lone factor outside of parentheses being multiplied into multiple terms inside the parentheses, then, ladies and gentlemen, we could take this lone factor of A and multiply it into all these terms inside the parentheses. We can say A gets multiplied by B, plus we can then say A gets multiplied by C. This is illustrating the distributive property of mathematics, okay? Very important property. Notice when you distribute, you remove the parentheses. It's kind of like you get these things out of jail. They're now out of jail. Pretty neat, huh? So where are we going to use this distributive property? I mean, why do we need it for solving equations? I mean, you know, we certainly don't need the distributive property to evaluate this numeric expression. Why not just do things according to the order of operations? Why do we have to distribute? That's a good question, especially for this problem. But ladies and gentlemen, you'll see when we get into variables in equations, variable expressions, we're going to have to distribute to get variable expressions out of jail from time to time. Okay, so let's see how we could employ the distributive property to solving equations. So let's try to solve this equation here. All right, let's try to solve 5 times x plus 9 is equal to, let's say 50. Okay, so we want to try to solve this equation for the variable x. That's our goal. So eventually we're going to have to get x all by itself on the left side of this equation. So how do we do that? Well, notice inside the parentheses is where order of operations would have us focus first. There's nothing we can do. These are not like terms. So we run outside the parentheses and we run into this factor of 5. In order to solve this equation, we have no choice, but we're going to have to get these terms out of jail. We got to get rid of these parentheses. And I have a question for you. What property is going to enable us to do that? What am I going to use? What property to get rid of the parentheses? The distributive property. We're going to take 5 times 1x. And what is 5 times 1x? That gives you 5x. Plus. Then we have to take 5 times 9. These arrows are a good visual cue. They show you that you've covered the bases. Please use arrows when you distribute. 5 times 9. And that's equal to 50 on the right. Hence, we have 5x plus what's 5 times 9? 45. Equal to 50 on the right. Everybody understand how I got my equation down to this? All right. Now, my ultimate goal is to get x all by its lonesome on one side of the equation and my answer or number on the other side of the equation. So what we're going to do here is we got to separate our variable terms on the left side of our equation versus our constant or numbers on the right side of our equation. So we now need to separate the variable terms from the constant terms. So the next move is to move this plus 45 over to the right side of the equation. How do I move a positive 45 to the other side of the equation? How do we undo addition?
Fraction.
So we're going to have to subtract 45 from the left side of our equation. And I'm going to also have to subtract it from the right side of my equation in keeping with the subtraction property of equality. The 45s drop out on the left side to 0. They're gone. And it leaves us with just 5x. Now, what's 50 take away 45 on the right? 5.
Mm-hmm.
Now, ladies and gentlemen, we are going to have to get x all by itself here. Okay. And how are we going to do that? Well, to finish this equation, to solve for x to get x by itself, we have to get rid of this 5 that's being multiplied by x. And that's going to lead me into the next section, which is section 10.2. So I'm going to take a little side jaunt through section 10.2. We're going to come back and we're going to finish this equation to solve for x. We're going to finish it up. So just leave that in your notes, leave a little space so we can finish this. 10.2 shows us the multiplication and the division property of equality. Just like there was an addition subtraction property of equality, there's a multiplication and division property of equality. It works essentially the same way as the other ones. Basically says this, ladies and gentlemen, that multiplication and division are inverses of each other. So that it says that if A is equal to B, then if I multiply the left side of my equation by some number C, just so long as I multiply the right side by the same number C, I'll still maintain equivalence. This is called the multiplication property of equality. As long as you multiply both sides of your equation by the same number, you still have equivalence between the left and the right side. In a similar fashion, if you divide both sides of an equation by the same number, you still maintain equivalence. This illustrates the division property of equality. Oh, we got to make sure we never divide by 0, though. Be careful there. So we got to specify the C can never be equal to 0. These are called the multiplication and division properties of equality. So let's come back to this equation and finish this problem now. How do I get X by itself? What's the undoing of 5 being multiplied by X? What's the inverse of multiplication?
Division.
Division. So to get X all by itself on the left side of this equation, to solve this equation, we got to get rid of the factor of 5. To do that, you know how we're going to do that? I'm going to do it up here. We're going to divide the left side of my equation by 5. And I also have to divide the right side by 5 in keeping with the division property of equality. Now, what happens to these 5s on the left side? They reduce down to 1. And 1 times X is better known as X. Our solution's on the other side. What's 5 divided by 5? 1, and we're done. We have solved this equation for X, and I've shown you all the steps, Now I'm going to allow you to use your calculator to take care of elementary operations, but I do want you to demonstrate some steps on your paper. I want you to show me how we're moving to the solution, ladies and gentlemen. I don't mind if you use your calculator to take care of the addition, subtraction, multiplication, divisions, but I want you still to show me steps as to how we're getting to our answer. The reason why I want you to demonstrate steps on your paper is because some of you are going to go onwards and take more math here at Mott or somewhere else. And trust you me when I say this, instructors do demand that you show your work in those courses in the future. And if you don't, you'll get the problem marked either partially wrong or all wrong. So I'm just kind of, getting you ready for those future courses. Like I'm going to start to, become organized on our paper and showing steps. Okay. All right, so does everybody understand how we solve this equation? First, we had to utilize the distributive property to get these terms out of jail. We then moved in the direction of separating our variable terms on the left side versus constants on the right. That involved next step of subtracting 45 from both sides. And then we had to get the variable all by itself on the left side, then by utilizing the division property of equality. And we were able to then accomplish our task there. Okay, able to accomplish our task. All right. Now, we may not have time for a classwork today, but if we do, I'll slip a couple problems in, but don't worry about it if we don't, all right? All right, let's try solving a couple more equations utilizing the division or multiplication properties of equality. I want to solve this equation for X. So how do I get X all by itself? Well, in order to do that, we need to understand what operation the -6 and the X are involved in. And what operation is that?
Multiplication.
It's understood it's multiplication here. Now, ladies and gentlemen, this is not saying X subtracts 6. No, it's not saying that. It's not saying this. It's saying -6 times X. So we don't add 6 to both sides of our equation. No. How do you undo multiplication?
Divide.
Division. So in order to get X by itself, we're going to have to divide the left side of our equation by a -6. But if I divide the left side by -6, I must also divide the right side of my equation by the same number to keep with the division property of equality. Now, what happens to these 6's here? They reduce down to what?
Just 1 or
One.
X.
Yeah, just 1. And 1X is the same thing as just X. 1 times X is the same thing as 1X, or we just say X. Now, what's 24 divided by a -6? A positive divided by a negative is always a negative. So this would be a -4. And that would be your solution to that equation. Questions how we did that? How we solved for X here. Now, this next problem is going to be a little bit trickier, but I'm going to try to give you one of each type of look here, so that we're going to be armed for this. What if we have this equation, we want to solve for X here? This gives us an entirely different look. Our goal is to eventually get X all by itself on the right side of this equation. But how do we do that? I see a negative sign in front of this fraction X over 4, and we're kind of mystified as to what to do here. Well, it's a well-known fact in mathematics, ladies and gentlemen, that when you have a negative fraction, it does not matter where you attach the negative sign. You're still going to have the same number. These are all equivalent to each other. Everybody see this here? Each one of these numbers are equivalent. So when you have a negative fraction, it don't matter if you attach the negative sign to the numerator or the denominator. They're still equal. That's important here because look at, I can attach the negative sign to the numerator or the denominator. To make my life easy, I'm going to attach it to the denominator. And therefore my equivalent equation to this is going to be negative 30 is equal to x divided by a negative 4. Now, ladies and gentlemen, how do I get x by itself? How do I undo the fact that x is being divided by negative 4? What's the inverse of division? What's the inverse of division?
Multiplication.
So we're going to multiply both sides of our equation by negative 4 to get x by itself. So here we go. We're going to multiply the right side of my equation by negative 4. And that's really understood to be negative 4 over 1, by the way. But I must multiply the left side by negative 4 in keeping with the multiplication property of equality. Got to multiply the left side by negative 4. Now, what's a negative 4 times a negative 30 on the left? Negative times a negative is always a
Positive.
So this will be positive 120.
Mhm.
And what happens to the negative 4s on the right side? Well,
Those cancel out.
if you're in the cross canceling, they cancel out or reduce out to 1s. But if you're not in the cross canceling, then multiply f cross, you'll have negative 4x and divided by negative 4. And then the negative 4 is reduced to 1. Do you agree? So neither way, whether you cross cancel the negative 4s out or multiply across first then reduce, you're going to get x equals 120. Ladies and gentlemen, we're done. We have solved for x there. X is equal to positive 120 there. Everybody see how I handle that equation? What if you have negative m is equal to 15? How would we solve this equation for m?
Divide by n.
Now, careful, we want to get m all by itself. Boy, it sure looks like m is all by itself. Is it though?
No.
No, we got a negative in front of m. When you got a negative in front of a variable, what does that mean? When you got a negative in front of a variable, it's really understood. It's like negative 1 times that variable. Understood. Everybody see that there? So when you got a negative m, it's understood to be negative 1 times m. Understood. It's understood to be that. So therefore, this negative m can be written as negative 1 times m. Now we know what to do. How do I get m by itself? How do I get rid of this negative 1 that's being multiplied by m? What's the inverse of multiplication?
Division.
I will divide both sides of my equation by negative 1. The negative 1's reduced down to 1 on the left side, and 1 times m is m. Now m is all by itself because we have a positive 1 in front of m. What's 15 divided by a negative 1?
Negative 15.
Here's your solution. M is equal to negative 15. That's your solution to this equation. You know, it checks out too. If you replace m with negative 15, isn't the opposite of a negative 15 equal to 15? Doesn't it work? The opposite of negative 15 is 15. It checks. It works. That must be the solution. Okay, that is the solution. All right, let's see what else we got here. All right, let's go to our textbook here and see if we can go to section 10.2 and just solve some more equations in the time remaining. We don't have much time left. Oh, by the way, how many of you actually look at the examples in the book? I would recommend you kind of take some time to study over some of these examples, ladies and gentlemen. I think it can only facilitate you better understanding the material. All right, now here's a tricky question here. Look at number 15 there. They want us to solve this equation, negative 5x equals 0. As simple as it looks, you wouldn't believe all the mistakes that are made with this equation. How would I solve for x here? How do I get x all by itself? Well, this is negative 5 times x. What's the inverse of multiplication? So I'm going to have to divide both sides of my equation by negative 5. The negative 5 is reduced down to 1 on the left side, and 1 times x is x. And what's 0 divided by negative 5? 0 divided by any number, ladies and gentlemen, is always 0. So the solution to this equation is 0. That's your solution. We're done. Check the answer out. Is -5 times 0 equal to 0? Does it work? Looks like it works, doesn't it? All right. Then we run into a problem where we have a fraction in front of a variable. If I got 2/3 times x equal to like, let's say 16, how would I solve this equation for the variable x? Well, I got to get x all by itself. But how do I do that? How do I get rid of this 2/3 that's being multiplied by x? What's the inverse of multiplication? Division. So what we could do, ladies and gentlemen, we could divide both sides of the equation by 2/3. We could do that, right? And when you divide the left side by 2/3, the 2/3 reduce down to 1, and 1 times x is x. But on the right side, you have to divide the 16 by the 2/3. You can use your calculator to do this if you want. That's going to be 16 over 1 times 3/2. Dividing by a fraction involves multiplying by the reciprocal of that fraction. Change division to multiplication, flip the second fraction upside down. Now, if you're not into cross canceling, 16 times 3 is 48. And what's 48 divided by 2? 24 is your solution. And we're done. So we solved that equation for x. We got 24. Everybody understand how we solve for x there? 24. We had to divide both sides by 2/3. All righty. Number 26. What would I divide both sides of my equation by for 26? What would I divide both sides of my equation by for 26? Since it's -2/5 times x, what would I divide both sides by?
2/5.
Not +2/5, but
-2/5.
yeah, you'd have to divide both sides by -2/5 to solve for x. What would you divide both sides of number 24's equation by to solve for a?
-3/4.
Not -3/4, just what? 3/4. Just 3/4, correct? Just 3/4. All right. Okay. Let's look at problem like number 30 here. They want you to solve this equation for x. I have a question for you. Does it look like we have any simplifying that needs to be done on the left side of my equation first before I start moving things from one side to the other side of the equation? What do you think, ladies and gentlemen? Think we should simplify the left side a little bit?
Yes.
Got any like terms on the left side that are screaming to be combined? All these are like terms that need to get together. So what is 7 minus 5 plus 8 of these x's? What does that give you? 7 minus 5 is 2. 2 plus 8 is 10. So we really have 10x is equal to 20. Now, how do I solve for x? How do I get x all by itself?
Divide by 10.
Divide both sides by 10.
Be 2.
These 10s reduce to 1 on the left. 1 times x is x, and x is equal to 2. You got your solution, and we're done. Now we understand how we solve that equation for x. First, we had to simplify the left side by combining like terms. There's going to be times when you have to simplify one and or both sides first. It happens. All righty. Okay. Now, notice there are some equations in here that actually have some fractions involved in them, aren't there? And fractions really are kind of a mess. They're kind of a pain. But you guys get to use a what? You can use a calculator. So like, it don't matter how messy these things get. Do you agree? We can still negotiate them. Problem number 67 looks like a real mess here, ladies and gentlemen, but I'm going to show you how to solve number 67. We have 1/2 m minus 1/4 is equal to 1/12 m plus 1/6, and we want to solve this equation for m. So the instructions are going to say solve. Well, we can work with the fractions if you want, since we got a calculator. That's not going to be a major issue. But notice we got m appearing on both sides of our equation, and that's no good. So what we have to do is we have to separate, ladies and gentlemen. We have to separate variables on the left side of our equation and our what? Constants on the right side. So I got to bring this 1/12 m over to the left side of my equation to join the 1/2 m. How do we do that algebraically? What equality property do we implement here to bring the 1/12 m over to the left? Is this a plus? This is a plus 1/12 m. How do I move a positive 1/12 m term to the other side of the equation? What's the inverse of addition?
Subtraction.
We're going to have to subtract off that 1/12 m from both sides of our equation. Got to subtract it off from the right side also. This step, as laborious and long as it is, ladies and gentlemen, I want to see this step because it's showing us that we're subtracting 12 m from the left, 1/12 m from the left side, and we're subtracting it from the right side. It's very important to show this step. Now, we need to combine these fractions here. What's 1/2 m minus 1/12 m? Anybody got a TI 30 or TI 34? What's 1/2 minus 1/12?
5/12.
Yeah, it's going to be 6/12 minus 1/12, which is 5/12. Thank you. So 1/2 m minus 1/12 m is going to be 5/12 m minus the 1/4 equals these 1/12 m's dive out on the left side, on the right side of your equation. They add up to 0. They're gone. They cancel out, leaving you with 1/6. We continue to separate. We got the m on the left side. We got to bring this constant over to the right side. How do I move a minus 1/4 to the other side of the equation to join the 1/6?
Positive.
Got to add it to both sides. So now we're going to have to add 1/4 to the left side. And now we have to add it also to the right side of our equation in keeping with the addition property of equality. Ladies and gentlemen, these 1/4 drop out on the left side to 0, correct? Negative 1/4 plus 1/4 is 0. So the left side collapses down to 5/12 m equal to, oh, help me out. What's 1/6 plus 1/4?
3/4.
Careful, do that again. 1/6 plus 1/4. 1/6 plus 1/4. You can do that on the calculator.
5/12.
Yeah, it gives you 5/12. So we got 5/12 over here. Now, one last move. How do I get m by itself? How do I get m all by itself here? How do I get rid of this 5/12 that's being multiplied by m?
Subtract. What divided?
Divide. We got to divide both sides of our equation by 5/12. Divide the left side by 5/12, and we got to divide the right side by 5/12. Hey, something interesting happens. These 5/12 reduce down to 1 on the left side, and 1 times m is m. What's our solution? What's 5/12 divided by itself?
1.
1 is your solution to that equation, and we're done. Ladies and gentlemen, we have solved a multi-step equation here. You know what? I get this feeling that we're going to have to do a lot of practice in solving equations. Do you agree? A lot of practice, ladies and gentlemen.
I've gotten the hang of it. I've done it in the past, so.
That's awesome. Wow. So everybody, Lydia could be our tutor for the class if you need help. See what you've done to yourself, Lydia?
Yeah, I guess I have.
My big mouth, you know? All right. Sorry about that, Lydia. I don't want to, I don't want to obligate you or anything, but yeah, no, thanks a lot. I mean, no, honestly, that's going to help. That's going to help your cause a lot that you've maybe played with these a little bit in the past. That's more power to you. There's no doubt about that. So,
Yeah.
All right. Any other questions, ladies and gentlemen? I worn out my time. I mean, I'm all out of time here. So I will begin to assign you solving some equations, and I got to get that midterm exam to you. And I will get it to you, ladies. I'm going to specify the due date on that, okay? So stay tuned to your email. Very important. Make sure you check it at least once a day, all right?
Okay.
I'll try to get the midterm exam to you tonight after I get home from Ann Arbor, okay? I got a couple classes down there that I got to deal with, all righty?
Okay.
Everybody got that, ladies and gentlemen?
Yes.
Okay, you have a good day. Have a great weekend, okay?
Thank you. You too.
All right, take care.
Bye-bye.